So today we're going to look at exterior angles and how they add up. You've already seen interior angles, right? Interior angles in a polygon, those are the ones on the inside here. And in any polygon, if you take the number of sides, in this case 5, you take away 2 from that number to get 3. That tells you in this case how many triangles I would get if I chop this up using diagonals from one point. And you'd multiply 180 times that number of triangles, 180 times n minus 2, to get the total number of degrees. In this case, I could figure out that there are 540 degrees in this pentagon, or in any pentagon for that matter. Well, exterior angles don't quite work the same way. Like if you look here, I've got the 53 degrees here showing up at the top in this addition. The 94 shows up there, the 51's there, the 70's there, and so on. And in this case, all 5 of these exterior angles add up to 360. And that's the case actually not just if I have a pentagon, but if I have a shape with more than 6 sides. I just added a side here, I'm still getting 360, right? Watch this number here, I'm going to add another side, still 360. And that's the case no matter how many sides you have. These sides will always add up to 360 degrees. Now, one important thing here is when we're counting the exterior angles, for each vertex, you only count one exterior angle. Right? You could, if you wanted to, draw 2 exterior angles, like one this way, one that way. They would be the same because they're vertically opposite. And if you were to add them like that, you wouldn't add up to 360. You'd end up getting 720. But really, you just need to consider one of them. And when you consider that, and you add those together, you'll always get 360. Now, you might be wondering why this is. Here, let me show you something else. Let's say this is a non-regular hexagon here. I want you to see all these exterior angles. They're different colors. If I shrink this shape down, I want you to see what happens to those vertices, to those exterior angles. Together, they all make a perfect circle. They all make 360 degrees, right? Now, that's visually, that makes sense, but you might say, well, that's just kind of a neat coincidence here. I'm not maybe satisfied yet as to why that always has to be the case. Well, think of it this way. Let's say this, I'm going to take away a couple of sides here just so that there's less addition for us to do here. I'm going to see and make sure the numbers actually add up. So let's say you're driving along a racetrack here. In this case, it's a pentagonal racetrack. And every time you get to a corner, you have to turn to stay on the track, right? So let's say this is the start-finish line here. You're driving along, you're driving along, driving along. Now you've got to make a sharp left-hand turn here, 97 degrees, to stay on the track. So far you've turned 97 degrees to the left, but you're on the track. So you keep going, keep going, keep going. Now to stay on, you got to make a 51-degree left turn this way to stay on the track. So far you've turned 148 degrees to the left. You keep going, you keep going, you keep going. Oh, if I don't want to go flying off here, I got to turn left again. Let me turn left. That's a 70-degree left-hand turn. Now I've turned left 218 degrees total. And here, if I make another sharp left turn to stay on the track like that, I've now turned 322 degrees total, 312, sorry, degrees total. Finally, I'm getting to the end. If I want to actually cross the finish line, not go flying off, I got to turn 48 degrees to the left here. And now I've turned a total of 360 degrees to the left. Since in every polygon, you're always going to end up pointing back the way you are on the racetrack, right? That's how a racetrack will work. The only way that makes sense is if you make a total 360-degree turn over the course of all of your left turns through the racetrack. So it's got to be 360 degrees. That's the only way that makes any sense for it to work that way. Now, where this gets maybe a little bit handier is if, these numbers are all kind of jagged numbers. They don't work very well together. But if you know that the total of all the exterior angles has to add up to 360, then as long as all of these angles were the same, you'd be able to tell exactly how many degrees there were in each exterior angle. And if they're all the same, that means you're dealing with what we call a regular polygon. So let's make this a regular pentagon. And you'll see that each of these angles is the same as each other, as it has to be for a regular polygon. And each of them is just 360 divided by 5. 5 is the number of sides here. So if you do 360 over n, that's your formula for the sum of the for the vertices, for the degrees in each exterior angle in a regular polygon. Let's try it with another polygon. Let's say I have 6 sides. If it's a regular polygon here, then I can take that 360 total, that's always got to be the case, divided by the number of sides, and it'll give me 60 degrees. That's the number of degrees in each angle. So in order to keep that in mind, here's the formula you want to know. If you want to know the total number of degrees in all the exterior angles of a polygon, then it isn't even really a formula. It's just this, 360 degrees. There's always 360 degrees in the exterior angles of a polygon. If you want to know how many degrees there are in each angle, in each exterior angle of a regular polygon, then as long as it's regular, you can take that 360 degree number and divide it by the number of sides. And remember, in this unit, we're always using n to represent the number of sides. So 360 over n, that's your formula for the exterior angle of a regular polygon. One last thing I want to show you, and this is kind of a little more complicated, but that when we've been talking about this 360 number, there is kind of a case where you won't get 360. But as long as you follow the right rules for calculation, you will. And that's that so far we've always been dealing with convex polygons. If a concave polygon comes along, then watch what happens here. I'm going to bend this vertex inside to make it a concave polygon. Now you see, the exterior angle is always defined as I extend one side past the vertex and then I get the angle here, like this is 122 degrees. But in this case, when you have a concave polygon, then your exterior angle that you get when you extend this side past the vertex is actually on the inside of the shape. And so if you're having an exterior angle on the inside of the shape, the only way that that makes sense mathematically is to define that exterior angle as a negative angle, which would be negative 85 degrees in this case. And so then when you add all these up, you still get 360, but only if you're counting this as negative. So that's kind of a case to watch out for. Another way you can say to yourself is just this rule always works easily and cleanly for convex polygons or for regular polygons, that these all add up to 360. If you're dealing with a concave polygon, you might be safer saying, well, you know what, I know that other rule for interior angles works for every polygon, convex, concave, regular, whatever. So if you just stick with your rule for interior angles, then this negative angle business isn't something you need to worry about. It does work, it's an added level of complexity that you don't see when you're dealing with convex polygons.